So we're going to continue with our work on functions. Now that we know our parent functions and what their graphs look like and what their domains and ranges and increasing, decreasing, and maxes and mins and symmetries and all that are, we're going to talk about making transformations on those functions. So first let's talk about vertical shifting. Vertical shifting is the transformation that I find students like the most. It makes the most sense. It's the most straightforward. So vertical shifting says if I have the graph of y equals f of x and I add a real number value to that entire function, then basically all that does is shift that function up in the plane in the positive y direction. And if I start with that function and subtract a constant from it, then it takes that function and shifts it down in the plane here a distance of c. So we have no problem with plus meaning going up the y-axis and minus meaning going down the y-axis. So I find students don't struggle with vertical shifting really at all. For instance, if we take our parent function, y equals x squared, and we add 3 to it, then all we get is that parabola that has a vertex on the origin, and we pick the whole parabola up and move it 3 units up in the positive y direction. And if we take that parent function and we subtract 2 from it, it picks that whole function up and takes it down in the negative y direction this many units, or 2 units. So again, vertical transformation, not a problem. Horizontal shifting seems to be a little more complicated for students. And it has to do with the negative positive thing going on here. If we have a function f of x, and inside the function machine itself, here we have our domain values, we put them in this function machine that manipulates it somehow and gives us all these range values. If we add or subtract a constant inside of that function machine, then it changes the outputs. And so students understand a horizontal shift looks like this. It's an operation that happens inside the function, not like vertical shifting that happens after the function rule has already been obtained. The problem students have with it is this whole minus means movement to the right of our function, and plus means movement to the left of our function. And so let me explain why that is true, because the quantity x minus c means the difference between where I started with x and positive c. The difference between x and positive c. So that is a positive movement along the x-axis. This is in the positive x direction. And for this notation, that is the difference between x, and negative c. So that's why it's movement in the negative direction. So let's look at this notation, and maybe that will help you. You may even need to make this notation a couple of times, and then it will be helpful. So if I told you that I wanted to translate x negative c, that's why this winds up looking like x plus c. So the difference between x and negative c, which is movement to the left horizontally, winds up looking like this. And I find that students don't like plus meaning movement to the left and minus meaning movement to the right. But you've worked with it long enough now, it's probably really not an issue for you anymore. So here is our parent function again, y equals x squared. There's our parent function. And inside that function notation, inside before the mathematical operation is done on it, we have moved x a distance of 4 to the right. remember this is x minus -4 inside that function machine. So the difference between x and -4, that's why it is a translation of this parent function 4 units to the left in the plane. So there's our new vertex point. And here, the difference between x, where x started at 0, and it moved in the positive x direction. So x minus a +2. So that's why we're moving to the right. We pick that vertex point up in the whole graph and move it 2 units to the right. So minus means move to the right, and positive means move to the left. So not quite as intuitive as vertical translation. So let's talk about reflecting graphs. If we are going to reflect a graph over the y-axis, again, it's really straightforward. If I have a function that's y equals f of x, and I graph that function, right here is y equal f of x. If I'm going to then graph y equals negative f of x, this negative right here says take every one of my outputs that was positive, and now every one of those outputs has to be negative. So that is a direct reflection right over that x-axis. Everything below the x-axis is negative outputs. Everything above the x-axis is positive outputs. There's positive y. Here's negative y. So when we have a negative on the outside of our function, we intuitively don't have a problem reflecting it over the x-axis. The problem seems to come for us when we put a negative again inside that function machine. And so let's talk about what that means. If I have f of x and I am going to put nothing but the opposite value in that function machine, this is the opposite value of x. Here's f of x. These are positive x values clearly that I've put in this function machine. So when I reverse that, then this says every positive x value that I put in there is now a negative x value. So I'm going to, that should be right there, I'm going to get the same output, but I have the opposite input that I had in my parent function. So when we put the x inside the function machine, the negative inside the function machine, that in essence is a reflection over the y-axis. So we're going to have reflection over the y-axis when we put the negative inside the function machine. We'll have a reflection over the x-axis when the negative is outside of the function machine. So let's look at some examples of that. So here is the parent quadratic function, f of x equals x squared. So I draw x squared, no problem. And when I put the negative in front of it, it says everything that was positive is now negative. So again, just a reflection right over that x-axis. When I put the negative inside the function machine, right here, like is done here, it takes that parent function and it says every positive input value that you put in there, let's say you put in 1, we're going to now put in -1, and this is what the output would be. And then we're going to put in -2, and then we're going to put in negative so on. So when we put negative values in there, it reflects it right over the y-axis. Now, the one thing that we'd have to worry about is that we could not put positive values in here. We couldn't put the negative of +1. We're going to have to put the negative of -1 in there, right? So that's why this is saying the domain of this function is all negative values up to and including 0. So for this particular function, the square root function, when we say that we are going to put input values in there, all of those input values better be negative, because we can't have a negative under that root sign. So that's why the domain of this function, when it gets reflected over that y-axis, the domain has to be all negative input values and 0. So let's talk about vertical stretching and compressing. When we add coefficients to our function, when we add a number in front of our function, y equals f of x, when we put some constant in front of that, it changes how those outputs perform based on the input. If I have y equals f of 1, which equals 2, then if I put a constant of 3 in front of that, then that takes that output and multiplies it by 3. So that is vertically stretching my function. That's going to vertically stretch the function where it goes way up and way down based on input values that behaved this way in the parent function, but they're going to behave differently in this vertically stretched function. Additionally, this is for input values, constant values greater than 1. But for fractional input values, which is what this means, any fraction between 0 and 1, let's say my favorite, 1/3, then that is going to vertically compress our function. See how now these outputs are now compressed from the original function y equals f of x. So it makes a difference what the value of c is. Multiplying by any constant in front of the function rule is not always going to stretch your output. Sometimes it could compress your output. So we need to pay attention to that. And that's vertically along the y-axis. So here, for instance, again, our favorite parent function, when we put a value greater than 1 in there, it is going to stretch those outputs, right? Here's the original parent function, but now our outputs are growing much quicker. When we put a fractional value as a coefficient, then our outputs are growing much slower. It's going to compress the graph of that parent function. And finally, let's talk about horizontal stretching. This is where we put that constant inside the function machine. So let's explore what happens when we put that constant value inside our function machine. So if we have our parent function and we take some constant value c and put it inside, our function machine, then we're changing the input values that this function is used to dealing with. And depending on whether c is a real number greater than 1 or some fractional number, we're going to get horizontal stretching or compressing of graphs. So let's talk about what happens on this when c is some real number greater than 1. So basically what this is going to do is this is going to shrink our graph because the outputs of our parent function, if we put a constant in there greater than 1, it's going to cycle through its range and its domain much quicker because this is going to force us to cycle through all of these x values much quicker when that's a constant value greater than 1. Now, if we put a fractional value in there from our parent function, it's going to make us cycle through these x values a lot slower. We're not going to get through all those values as quick because we're going to be taking 1/3 or 1/2 or 1/4 of the original x values we put in from our domain that function rule worked on. Again, it's kind of seems to be counterintuitive that a fraction makes it a longer graph and that a whole number makes it a shorter graph. But when you think about what's happening inside that function machine, it makes all the sense in the world. So we'll look quickly at a graph here. The graph of y equals f of x is shown right here. This is a normal graph. So when we double the x value that we're putting in, it goes through there very quickly. When we have it, it takes longer for it to go through its behavior. So this is the end of this video. We'll talk really quickly. There'll be another short video. We'll talk about even odd functions.